Okay. Yeah, we had the midterm examination in the last Wednesday, and this is the this is your midterm tentative midterm standing. This is the point that you had from the midterm examination. Out of 100 point on the midterm examination, and this is the total sum that I calculated based on your online participation for 10%, like the syllabus said, and 10% offline attendance and participation, question and answers in the class, and this is 20% for your homeworks and quizzes and PBL reports, and you had the 15 point. I think this is this is the participation part. 15 point given here. This 15 point and this 85 point were added to up the 100 point on your midterm examination. Okay. And it was scaled that the syllabus said the midterm exam counted for 20%, and your comprehensive final exam will be counted for 30%. So now we only have a midterm examination, so I gave a 50% percentage on your midterm examination. So I rescaled this. So I added this 10 point online, 10% offline participation, and 20% for your homeworks and quizzes and PBL reports, and 50% on your exams. So it makes 100. That gives you this added point out of 100. So, yeah, and also I gave you for four students for graduate students who taking this for pass and fail, and these are your standing. Today I made my office hour open for you fully. So yeah, you were asked to meet me to pick up your exams sheet. Okay, it is ready here. So let's go to look at your exams. So we can find possible ways to improve your presentation on your exam sheet, and to improve your scores. And here, okay, so I made it. So today, yeah, we're gonna cover section chapter 7, section 7.1 to 3. Before we start the lectures on chapter 7, I uploaded the solution sheet for our midterm examination here. So let's review our problems and solutions. So 85% for the offline and participation 15 point, your separate sheet, it will be added as 100. Okay, here I made this. Here, as you see, all others are true, like you have learned from the class. And here, the vectors, the number 4 here, the vector in this solution space of AX is equal to 0 are all orthogonal to not column space, but row space, because the vector addition goes to these rows and the vector B like this. So that inner product of the row vector of the coefficient matrix A and the vector X is equal to 0. So those two vectors are orthogonal. So this should be low. here, second, for a set of natural numbers, the commutation here, everything's are true except when you permute, if tau be a permutation by switching any two numbers from a given permutation sigma, then sign should be changed. All did well on this. Third part. Here everything else are true except this. In Rn, if you have a set of vectors which is more than n vectors, then that should be linearly dependent. That's true. And number 4 here. If U cannot be expressed as a linear combination of V and W, then the three vectors are linearly independent. This is not true. If V and W are linearly dependent, then when you add one more vector, which is the set cannot be linearly independent. So that was the case. Many were missing this part. Here, number 4, if t is if and only if corner of t is equal 0, when the linear transformation t from Rn to Rn is a linear transformation. If n is equal to m, then this is a true statement. But when n is not equal to m, then it may not, this statement may not be true. Okay? Any questions? Ms. Kim? Next, second part. State more than 5 things that you know or find or you can do it after you studied 2 months of linear algebra from our class. And many of you did very well on this. Yeah, you wrote what you have learned and what you can do now after you studied the first 6 chapters of linear algebra. Next, I asked you to choose 5 and mark those and write what you know about it as much as you can. So I listed out more than 10 concepts theorem here, and you wrote it well on this, except a couple. But most of you did well. Yeah, you did define minors and cofactors. You did define, you did write the fact that you know about adjugate of a given matrix, and you did write on cofactor expansions, and some did write on the Cramer's rule in detail, and some did write on eigenvalues and eigenvectors and eigenspaces and standard matrices, etc., linear transformations, etc. And for first part, find and compute or explain. And here, I gave a sample exam on this, and most of you did well on this because most of you have done it before, except 1 or 2. And so you now here, if you have this matrix, which is new compared to the sample exams, then in any of the Sage cell or Sage server, Sage cloud or whatever, there are many choices that you can do. And if you copy this matrix, if you define a matrix, and first here you can type it, but you can randomly generate a certain matrix, 3 by 5 or 10 by 11 or whatever, and then you can make changes of those generated matrix to of the set. So you don't really type this when you need it. You can get some help with some code, and this means generate 100 by 100 random matrix over Q. This is the meaning of this code. Sage code based on Python computer language, and define a vector y, and then you here this means find the inverse matrix of A. And so you should write find the inverse matrix of A. This means find the characteristic polynomial of A, and this you should write this. The matrix A has can have right eigenvector and left eigenvectors. The definition that you have learned was the definition of right eigenvectors. So because Ax is equal to lambda x, there x is on the right side of the A. You can also find the mu x is equal to xa. The vector x from there, dedications are called the left eigenvectors of A. But we didn't define this, so you should write this command in order to have the eigenvector that we have learned. Okay. Here, so if you read this command, here we have a determinant of A here, which is minus 432, and we have the inverse matrix of it, and we have a characteristic polynomial of this 5 by 5 matrix, and we have this gives us 5 eigenvalues of a given matrix, and this is 5 eigenvectors and corresponding eigenvalues. So here we have 5 eigenvalues here. So what is the algebraic multiplicity of eigenvalue 6 of A? Here, eigenvalue 6 is here. So this one is the algebraic multiplicity, and the number of eigenvector in here is the corresponding geometric multiplicity. The number of linear independent eigenvectors corresponding to this eigenvalue will be listed here. Here we only have one, so geometric multiplicity of eigenvalue 2 is 1, because we have only one linear independent eigenvector here. If you have 2 or 3, then it means you have 2 or 3 here. And what is the corresponding eigenvector of 6 here? So we have only one linear independent eigenvector corresponding to 6 here. So everybody know it. Okay, Orkan, you know it. You should be able to find it. Okay, Miss Kim, you know it. You can find the eigenvalues and eigenvectors and algebraic multiplicities and geometric multiplicities too. Okay, good. And determinant and inverses. If you, this is not only work for 5 by 5 matrix. It also work for 100 by 100 or 1000 by 1000 as well. That you cannot do it by your hand. Okay, you should be able to do it now. Mohammed, you can do it. Okay. And I asked you to choose 5 and give a sketch of the proof, or find or explain or fill the boxes on problems such as this. Explain. I didn't ask you to prove it. I just asked you to give a sketch of proof. So if you can explain this in a mathematical way with the right logic, then you got full credit on this. Here explain W2, why W2 is not a subspace. If you want to show this is a subspace, then it should satisfy a two-step subspace test. So you checked it and you found the vector addition of the arbitrary 2 vectors from W2 may not be in W2 in general. So it's not closed under the vector addition. So this W2 is not a subspace. With this in detail, I gave you another one, which shows, explain why the set of all linear combination of S is a subspace of Rn. And so what you have to show is this satisfies two-step subspace test. So you did choose two arbitrary vector from W, which can be written as a linear combination of these vectors, because this is a span of these vectors. So all the elements there should be written as a combination of linear combination of the given vectors in S. So if when you add those two, as you see, this is another linear combination of this set of vectors, Xi's. And the scalar multiple of that is also a linear combination of the vectors in S. So they are closed under the vector addition, and this is closed under the scalar multiplication. So it satisfies the two-step subspace test. So it is a subspace. Got it? Okay, Buck. You got it? You can show whether the given set of vectors are linear, the subspace or not, by checking these two conditions. Okay. Next, when you have the vectors like that, we move to linear transformation T. When you have a linear transformation T and S like this, and find the standard matrix of the composition of those two linear transformation. So from each, you can find the standard matrix, and the standard matrix of the composition function is just product of those two in the proper order. Okay, so S here and T is here. So T is on the right, and S is next. So, and with those ideas, I gave you one more question on the compositions. And I gave you a linear transformation, find the standard matrix of this, and you found you can find the standard matrix for each T1 and T2. Then all you have to do is the same thing on this. Okay, find the number of leading variables and free variables in the solution set of the following system. As you see here, there are if you write it in the coefficient matrix of this, then you will see these are leading variables. You have 1, 2, 3 leading variables, and you have 2 free variables. So 3 and 2. Okay? This by Gaussian elimination, you will have the form like this always. Then you can always characterize the leading variables and free variables. Can you read it? Okay. Let the characteristic polynomial matrix, if this is a characteristic polynomial, then the eigenvalues of the matrix A cube should be the cube of each eigenvalues of A. Eigenvalues of the matrix A to the 2001, then it should be the power of each eigenvalues of the power 2017. And linear system AX is equal to B has a solution if and only if length should be the same. Okay, this was in the examples, the exercise problems of the textbook. Actually, we will cover it once more in chapter 7. Here, as you see, if we have this, then the linear system of equations AX equal B can be written in this way. So, if this has a solution, that means there exists Xi's that satisfies this, isn't it? Okay, which means this vector B can be written as a linear combination of these vectors. Okay, okay. This is what. Then, which means the linear combination of these vectors. What that means is the whole set of linear combination of these vectors are exactly same as the column space of the matrix A. Okay? Because the linear combination of the column vectors of A, set of span of column vectors of A, which means B is not linearly independent, so it does not make any effect on the length of a matrix when you add it to the matrix A, because B is linear dependent of each columns, so the length does not changes. So this means this. So this vice versa. If you start from here, which means if these two lengths are same, that means B is linearly dependent, which means B is in the column space of A. So B is a linear combination of the columns of A. That means there exists xi's that satisfies this, which means that X is a solution, so if and only. If Ax is equal B and Ax equal C have a solution, then Ax is equal B plus C has a solution. Suppose x1 and x2 are solutions of each, then that satisfies this. So if you add those two and put it on the equation, then as you see, that satisfies this equation, which means x1 plus x2 is also a solution of the given linear system of equation. Okay, so yeah, Ax equal B plus C always has a solution whenever these two equations have a solution, because when you add any solution of each, then they will be a solution of this. This is also will be used over and over again. And let A be a square matrix, and k times of one row is added to another row of A, and name it as B, then those determinants should be same. That is the same as saying that the determinant, when you do the third type elementary row operation on the given matrix, there's no change on the determinant, because as you see here, the determinant of B is this, like you see, but determinant of B can be written as this. It can be split out like this, but this part is just, this part should have two same rows, this matrix. So determinant of a matrix which has two same rows, then determinant should be 0. So this part is going to be 0. What's left is just the determinant of A. So determinant of B is same as determinant of A, which is this. So when you do the third type elementary operation, there's no change on the determinant. Next, this is also easy one, and determinant of this A and B are same if they are similar. Okay, this can be written as this. This can be split out like this. This is the multiplicative property of determinant, and then you can change the order, because those are just scalar number, scalars. So you can spare it. You can mix it like this. Then this is identity matrix whose determinant is 1. So that should be same. So it's always work. We're gonna learn deeply on this, on the using of this similarity relationship over and over again. Okay, here this tells about how this image of T is a column space of A. Show image of T. Then image of T is a column space of A. Why? A can be written as this column with these column vectors. Okay, and then any vector x, for any vector, this Ax can be written as this, which means image. The T of x can be written as Ax. So this any image can be written as a linear combination of column vectors, isn't it? So that means the image of T is in the span of the column vectors, and the other inclusion part is trivial, so they should be same. I think that's it. And then most of you have your solutions. You filled it out like what you did. So as you see, for first chapter, I asked you, in order to pass this course, you should make questions and answers regularly. The minimum requirement was given. In order to pass, you should meet the minimum requirement. Okay? You don't have to make 100 or 200, but that's the bottom line. You should ask and question. You should participate. This is a course prepped learning class, and that active learning is required. Okay, so for those who has about 40 will had the full credit, but those who have less than 25 or something got a very less point on this. This is required. And online attendance, and offline attendance, and you made it. So this was counted 15 points. Okay, and also, I gave you the sample code so you can use it. I told you, I gave you the things that you could use it. I gave you those codes there. So I also gave you what that means. So I think that's it. Any question on the midterm examinations? Mohammed? Okay, then good. Next. And this I have graded. Your solutions, your exam sheets like this, and I will hand this over to you when you have a personal interview with me after class. So so you will see what was the point that you got and what was the point you deducted. Okay, so I think that's it. And next, we're gonna start chapter 7. So we have about 10 minutes. We have 15 minutes before we start the lecture. So try to read the lecture note today and make questions or answers. I found the Mohammed and Brooke and Orkan made the questions before they come to class. So others should try to answer on those questions if you know before we start. Okay, any questions? Okay, then let's take a time so you can get prepared for today's lecture on chapter 7.